Can true perfection ever be achieved in rocket design? Or is it the relentless pursuit of improvement that truly defines success? SpaceX's Starship challenges this very notion, with each new iteration becoming bigger, better, and more advanced, not only in raw power but also in the refined details of how it's built. In fact, when SpaceX completes its Starship version 3, it's expected to be the most advanced and impressive variant in the company's fleet, not only delivering immense power, but also boasting a sleek, futuristic appearance straight out of a sci-fi movie. And one of the key elements contributing to that striking beauty lies in its weld seams. So, what exactly Starship version 3 welding look like? Or could it even reach a point where welding is no longer necessary? Let's find out on today's episode of Alpha Tech. But first, we need your support. Our next goal is 150,000 subscribers. Let's hit the subscribe button and you won't miss any of our episodes. Of course, we'll strive to improve in every aspect. Thank you very much. The ambition to expand SpaceX's Starship program has existed ever since it was first unveiled as a conceptual design. The second-generation Starship has already completed 2 flights and 5 prototypes, which makes the upcoming Starship version 3 the most highly anticipated development right now. Even before discussing its technical aspects, the appearance of Starship version 3 stands out. It's a highlight even at the conceptual design stage. But why is that? Does visual aesthetics really matter? The answer is yes. Beyond technical reliability, SpaceX places significant emphasis on the visual appeal of the Starship rocket. Setting aside its bullet-like shape, the beauty of these spacecraft can be appreciated through their sleek, polished exterior. Who would have imagined that the gleaming mirror-like Starship we see today once looked so rough and unfinished? If you're just now learning this, I hope you won't be too disappointed by those early images. That was indeed the very first version of SpaceX's Starship. And compared to how it looks now, the difference is striking. To achieve the smooth, polished surface of today's Starship, and likely an even more refined Starship version 3 in the future, where visible weld lines may completely disappear, SpaceX has had to continuously improve and innovate. Specifically, the company has worked tirelessly to refine and upgrade its welding techniques to assemble the rocket's sections. Welding is a critical process for joining metal components in a rocket engine, which must withstand extreme temperatures, pressure, and vibrations. However, this isn't always easy, as it depends on many factors such as the welding method, the skill of the welder, and the unique materials used in rocket construction. In the early stages of SpaceX's ambitious Starship project, welding quickly emerged as a particularly challenging and crucial aspect. Initially, SpaceX had what seemed like a perfect plan: to build Starship from carbon fiber composites in California, where most of their workforce was based. Carbon fiber is renowned for its exceptional strength, so the decision appeared logical. However, a sudden change occurred when a stainless steel Starship prototype appeared in Texas. While this move was surprising at first, the choice quickly proved its worth. First, in terms of heat resistance, carbon fiber begins to degrade at 200 degrees Celsius and would require a thick heat shield to withstand the 1,600 degrees Celsius of re-entry temperatures. In contrast, stainless steel naturally offers much higher heat resistance and only needs a thinner heat shield. In terms of cost, stainless steel is about $3 per kilogram compared to $150 per kilogram for carbon fiber. On top of that, working with steel is far simpler and far more flexible. Producing 9-meter-wide sections from carbon composite would have required an unprecedentedly large autoclave. Interestingly, the idea of a stainless steel rocket isn't entirely new. NASA built the Atlas rocket in the 1960s using ultra-thin stainless steel, so thin, in fact, that it had to be continuously pressurized to prevent collapsing under its own weight. Beyond the challenge of choosing the right material for Starship, SpaceX also struggled with the welding skills and techniques required. The company's first welding team, recruited from a water tower manufacturing company with little experience in aerospace, faced significant difficulties welding the 4.5mm thick 301 stainless steel plates. The early versions of Starship used a welding technique called flux cord arc welding. This method involves running an electric current through a wire, creating an arc between the wire and the metal to fuse them together. The molten metal fills in any gaps or imperfections. In flux cord welding, the wire is coated with a combustible material that releases shielding gas to protect the weld from oxygen in the air, which could cause rust. While this method is effective in controlled environments, SpaceX ran into challenges because they were working inside a large tent rather than an actual factory. Many of the welds were done outdoors by relatively inexperienced workers, leading to less than ideal results for Starship's appearance. The welds on the first prototype, known as Mark I, showed signs of corrosion, cracking, and rough edges. To improve them, SpaceX ground the welds down until they were flush with the surface. This wasn't just for aesthetics. It actually made the welds stronger. Sharp edges and small cracks can lead to bigger problems when Starship is pressurized. Smoothing the surface eliminated these issues and reduced the risk of weld failure. Ideally, each weld should be as strong as the surrounding metal. However, Starship's first tests proved this wasn't the case. The Mark I prototype exploded after a horizontal weld failed, causing the bulkhead to separate. To address these challenges, SpaceX made significant improvements with the next prototype, SN1. They use thinner stainless steel sheets for each ring, reducing the amount of welding required. They also switched from 301 stainless steel to 304L, a material much more resistant to corrosion during welding. At this point, they also upgraded to tip-TIG welding, which allowed them to have better control over the weld pool. Everyday Astronaut, in a tweet in 2019, asked Elon, "Is there any substantial difference in welding manufacturing techniques between these bulkheads and Mk1, Mk2? Also, LOL." And Elon Musk replied, "Almost everything is different. These parts are stamped versus manually bump-formed and tip-TIG welded versus flux core. Higher precision, its stronger joints, and 20% mass reduction." Since then, each ring was made from thinner single sheets of stainless steel, which required much less welding. Alongside adopting the tip-TIG welding method, SpaceX also introduced laser welding for specific parts of the Starship spacecraft. Laser welding, known for its precision and flexibility, offers unique advantages in certain applications, complementing the capabilities of the tip-TIG technique. By incorporating laser welding into its welding toolkit, SpaceX further diversified its welding capabilities, allowing the company to tackle a wider range of welding challenges skillfully and effectively. With laser welding, heat is more concentrated and penetrates deeper into the metal, allowing entire ring sections to be welded in a single pass. However, to truly enhance the strength of each weld, an additional process is required. You see, when Starship's stainless steel is manufactured at SpaceX's facility, it undergoes a process known as cold rolling. This involves passing the metal through a series of rollers to compress and stretch the metal's grains. This makes the material harder and stronger. However, during welding, the heat softens the metal in that area again. This is where SpaceX's large peening machines come into play. Peening involves hammering the welds, compressing them until they match the hardness of the surrounding metal. This process also smooths out the weld surfaces and improves their appearance. But will Starship ever achieve a perfectly mirror-like surface? To answer this question, we can look at Chicago's famous sculpture, the Bean. Made from multiple stainless steel plates, this structure underwent an 8-month-long polishing process, involving a team of 24 people using a variety of abrasives. To achieve a similar finish on Starship, the entire spacecraft would need to go through a comparable process to remove every visible seam around its welds. Could this be the look of Starship version 3? Let's wait and see. SpaceX also employs another welding method for its Starship and Super Heavy rockets, a technique that sets it apart from other companies, called friction stir welding, FSW. FSW is a unique metal joining technique, unlike conventional methods like gas or arc welding, in that it is a solid-state welding process and doesn't require any of the materials being joined to be melted. Instead, the metals are softened enough that they can intermingle at the surface with a bit of mechanical assistance. This method results in exceptional mechanical properties such as high fatigue strength and hardness, while leaving minimal defects in the welded area. Additionally, it reduces material waste and requires lower surface finish demands. Perhaps one of its most praised benefits is that it produces no harmful gases, making it an environmentally friendly process. SpaceX's design engineers have applied FSW to join the internal fuel tanks in their rockets, critical components for propelling the spacecraft after it reaches space and stabilizing it in orbit. The reasoning behind this application is clear. The fuel tanks of a rocket this powerful demand significant structural strength, something traditional liquid-state welding methods or non-permanent joints like rivets couldn't reliably provide. The development of welding techniques in SpaceX's Starship project has occurred in parallel with strategic changes in material selection, both having a considerable impact on weld quality and durability. One of the most notable shifts was replacing stainless steel 301 with stainless steel 304L, a decision driven by the pursuit of stronger, more corrosion-resistant welds. 304L stainless steel also holds another advantage over both 301 and standard 304, its low carbon content. When exposed to high temperatures, such as during welding, chromium and carbon can react to form areas susceptible to cracking and corrosion. SpaceX's motivation behind transitioning from 301 to 304L stainless steel seems to be entirely welding related. 304L far outperforms in corrosion resistance, particularly beneficial in the extreme low temperatures that are an inseparable part of space exploration. In such harsh conditions, 304L stainless steel has demonstrated impressive strength and resilience, significantly outperforming 301. This superior resistance to brittleness and deformation at cryogenic temperatures plays a crucial role in preserving the structural integrity of Starship's welds, protecting against the risk of failure during space missions. SpaceX is currently in the process of producing Starship V3, incorporating several design changes while laying the groundwork for the upcoming V3, a massive version expected to reach a height of 150 meters. In these new iterations, durability remains a top priority. Since Starship is being designed for deeper space missions rather than just achieving orbit like V1, it will have to endure increasingly harsh conditions. In particular, re-entry procedures will expose the spacecraft to extreme temperatures, demanding stronger designs and materials. After 6 flights, Starship version 1 has demonstrated steady improvements, especially in handling the challenges of atmospheric re-entry. However, achieving full recovery of the vehicle remains difficult, highlighting the ongoing need for enhancements in manufacturing methods. Encouragingly, the first prototypes of V2 have already shown significant improvements. A side-by-side comparison of the nose cones from V1 and V2 reveals a major upgrade. The welds on V2 are nearly invisible, creating the impression of a seamless, unified structure. This not only indicates improved structural strength, but also showcases advances in welding technology. This points to a future where Starship version 3 will almost certainly feature a sleeker, more durable appearance than anything we've seen so far. But durability is only part of the equation. SpaceX is also focusing heavily on reusability, working to ensure their rockets can complete multiple flights. Advanced welding techniques will play a key role in achieving this by reducing structural stress and streamlining refurbishment processes. In the early days of the space age, no one thought bigger than Wernher von Braun. In the 1950s, long before Apollo made its historic landing in 1969, von Braun was already envisioning lunar missions on a much grander scale. His concepts for lunar landers weren't modest two-person vehicles designed to save weight. They were massive spacecraft capable of carrying 10 to 20 astronauts at a time, along with up to 60 tons of equipment and supplies. These enormous landers would descend to the lunar surface in their entirety and return to orbit without leaving hardware behind, aiming to establish permanent outposts rather than brief visits. And all of these ideas were distilled into the Nova rocket design at the time. This enormous rocket was conceived to dwarf even the mighty Saturn V in size and power. However, despite its impressive specifications and potential, Nova never progressed beyond the drawing board. Today, more than half a century later, a new contender has entered the conversation: SpaceX's Starship. Although originally conceived as a Mars transport vehicle, Starship shares striking similarities with von Braun's bold ambitions: immense payload capacity, full vehicle landings, and the potential to establish a long-term human presence on other worlds. This has sparked huge excitement in the space community and raised the question: Could Starship evolve into a modern realization of von Braun's long-abandoned Nova rocket concept? Well, it would certainly be a spectacular variation if it ever came to life. And to better understand what Starship might look like when applying the Nova concept, let's first take a closer look at the original Nova rocket itself. Nova was a three-stage super heavy launch vehicle, slightly taller than Saturn V, but far more imposing in diameter. While Saturn V's first stage measured about 10 meters across, Nova's massive first stage would have stretched to 15 meters in diameter, making room for colossal fuel tanks and an impressive array of engines. The rocket's first stage was designed to carry 8 F1 engines, the same powerhouse engines used on Saturn V, but in a larger cluster, delivering a staggering combined thrust of nearly 14 million pounds. The second stage was no less formidable, equipped with 8 J2 engines, providing over 1.8 million pounds of thrust. This immense lifting power would enable Nova to carry payloads and crews far beyond what Saturn V could manage. Its intended capabilities included landing 10 to 20 astronauts on the Moon in a single mission, along with 60 or more metric tons of cargo, including habitat modules, rovers, and life support infrastructure. Unlike the Apollo lunar module, which was designed for quick visits, the hardware Nova could deliver would have supported extended stays and the early development of permanent lunar bases. The Nova program, though ultimately abandoned, represented the kind of bold, visionary thinking that helped shape the early days of human space exploration. That same spirit continues to this day with the grand ambitions of Elon Musk, who has positioned SpaceX's Starship as a spacecraft truly capable of fulfilling this long-held dream of interplanetary travel. However, in many ways, Starship goes far beyond what Nova was ever designed to achieve. Starship's fully reusable, two-stage architecture features the Super Heavy booster as its first stage, powered by 33 Raptor engines. Collectively, these engines produce over 16 million pounds of thrust, exceeding the theoretical 13.9 million pounds of thrust from Nova's 8 F1 engines. The second stage, Starship itself, carries 6 vacuum-optimized Raptors, delivering 2.8 million pounds of thrust, more than double the output of Nova's second stage, which relied on 8 J2 engines generating around 1.86 million pounds. Another key advantage lies in Starship's use of the Raptor engine, a next-generation methane-fueled engine designed for high efficiency and deep throttling capability. Raptors offer superior thrust-to-weight ratios and higher chamber pressures than their 1960s counterparts, enabling Starship to achieve remarkable performance with fewer engines and improved reusability. Given these specifications, there's a growing argument for modifying Starship into a Nova-class vehicle by expanding its capabilities, perhaps by increasing tank size, rethinking materials to reduce weight, or adding an upper stage tailored for lunar or deep space missions. Starship could become the modern realization of the Nova concept. However, if Starship is to become a true Nova-class variant, it must first reconsider the materials used in its construction. One of the most debated aspects of Starship's construction is its use of stainless steel for the airframe, a decision made for its durability, cost-effectiveness, and resilience during atmospheric re-entry. While stainless steel offers important advantages, it comes at a cost: weight. Despite being narrower than Nova Starship's first stage measures, 9 meters in diameter, compared to Nova's 15 meters, the fully fueled Starship stack is heavier than Nova. Even when empty, Starship tips the scales at around 300 metric tons, while Nova would have weighed roughly 258 metric tons when dry, and that's including Nova's third stage. This additional mass compromises payload capacity and overall mission efficiency, requiring larger propellant reserves and more powerful engines to compensate for the extra weight. This weight penalty raises a compelling argument for reconsidering SpaceX's original material choice: carbon fiber composite construction. While significantly more expensive and technically demanding to manufacture at the scale required for Starship, carbon fiber offers enormous weight savings compared to stainless steel. Reducing Starship's dry mass would dramatically improve its payload-to-orbit capability, delta-V reserves, and mission flexibility, potentially making it a much better candidate for Nova-class missions to the Moon and beyond. If SpaceX were to revisit this earlier design path or develop a specialized, lightweight variant of Starship for lunar operations, it could transform the vehicle from a powerful Mars-bound transport into the fully capable, multi-destination workhorse Von Braun once imagined for Nova. In addition to increasing its size and modifying its construction materials, Nova Starship would need to incorporate a third stage, a strategy Wernher von Braun himself once advocated for deep space missions. Thanks to Starship's massive payload bay, the idea of housing a powerful upper stage within the vehicle isn't just feasible, it's actually highly practical. Modern upper stages, like the Centaur 3 used on United Launch Alliance's Vulcan rocket, can easily fit inside Starship's cavernous payload bay. A Centaur stage, with its slender profile and efficient RL-10 engines, would offer valuable flexibility for translunar or interplanetary missions. In fact, by clustering 4 RL-10 engines, a modified Centaur upper stage could deliver about 96,000 pounds of thrust, a respectable figure for today's standards. However, when compared to Nova's planned third stage, powered by a single J2 engine, Centaur's performance falls short. The J2, which burned liquid hydrogen and liquid oxygen just like Centaur, generated a far more substantial 232,000 pounds of thrust. This considerable gap highlights a limitation in the current upper stage technology when pursuing the kind of heavy lift, deep space capabilities envisioned for Nova, or a modified Starship. To truly match or exceed Nova's ambitions, any third stage added to Starship would likely need to move beyond current Centaur-class designs. This might involve reviving high-performance engines like the J2X, which NASA developed and later shelved, or pursuing next-generation nuclear thermal propulsion, which is already on NASA's roadmap for near-future deep space missions. Another thing Starship would need to adapt in order to become a Nova Starship is its choice of propellant. As space agencies and private companies set their sights on establishing a sustainable human presence on the Moon, the choice of propellant becomes a critical factor in mission design. For lunar operations, hydrolox, a combination of liquid hydrogen, LH2, and liquid oxygen, LOX, remains the most practical and efficient option, especially when considering future in-situ resource utilization, ISRU. One of the Moon's most valuable natural resources is its vast deposits of water ice, primarily located in permanently shadowed regions near the lunar poles. This ice can be mined, purified, and split through electrolysis to produce both hydrogen and oxygen, enabling the creation of hydrolox fuel directly on the lunar surface. This capability would dramatically reduce the need to haul fuel from Earth, lowering mission costs and increasing the feasibility of long-term lunar operations. In contrast, methane-based engines like SpaceX's Raptor are optimized for Mars missions, where methane can be synthesized from atmospheric carbon dioxide and subsurface water ice via the Sabatier process. However, the Moon's lack of a carbon-rich atmosphere makes methane production impractical. Without the ability to create methane in situ, lunar missions relying on methalox propulsion would face significant logistical challenges for return trips and surface operations, requiring all return fuel to be transported from Earth, an expensive and limiting proposition. For this reason, upper stages and landers intended for sustained lunar activity are better served by hydrolox engines, which not only offer superior efficiency in the vacuum of space, but can eventually be refueled on the Moon itself. Integrating hydrolox propulsion into Starship's architecture, or incorporating hydrolox-powered upper stages for lunar missions, would align far better with the long-term vision of self-sufficient lunar infrastructure and permanent outposts. Ultimately, converting Starship into a Nova-class heavy cargo transporter would unlock significant advantages for deep space missions, most notably in cargo capacity and mission simplicity. A Nova-class variant of Starship, whether through increased thrust, the addition of a third stage, or a combination of both, could deliver 68 metric tons or more to a translanar injection, TLI orbit in a single launch, without the need for in-space refueling. This capability would immediately surpass the performance of NASA's Space Launch System, SLS, which currently offers a maximum of around 38 metric tons to TLI. Such a leap in capacity would dramatically streamline lunar missions, With a single launch, Starship could transport larger, fully equipped lunar landers, heavy cargo, and crews of multiple astronauts, potentially achieving the ambitions of the early Artemis missions and beyond in far fewer flights. And with fewer launches, SpaceX could minimize the number of in-orbit refueling operations needed. Although SpaceX's current Starship architecture is groundbreaking in its ambition, one of its biggest challenges lies in its on-orbit refueling strategy. To complete a single lunar mission under the current plan, Starship would require 10 or more dedicated tanker flights to transfer the necessary fuel into orbit before committing to a translunar burn. While this approach is technically feasible, it introduces considerable operational, logistical, and political complexities. From a logistical standpoint, launching the largest rocket in history repeatedly in a short time, frame demands an unprecedented launch cadence, precise coordination, and exceptionally reliable weather and ground conditions. This places immense operational pressure on launch facilities such as Boca Chica, Texas, where concerns about environmental impact, safety, and disruption to local communities have already attracted attention. Scaling this up to dozens of launches per lunar or Martian mission risks amplifying these challenges, potentially slowing progress and increasing opposition from the public and regulatory bodies. This is precisely why a modified three-stage Starship system, especially one approaching Nova-class performance, could dramatically ease these burdens. Moreover, if designed with partial or full reusability for all stages, this architecture would preserve SpaceX's cost-saving objectives while making large-scale lunar exploration and eventual base building far more practical and sustainable. In essence, moving toward a multi-stage Nova-class Starship could streamline operations, improve mission reliability, and strike a better balance between exploration ambitions, launch infrastructure demands, and public accountability. If previously hot staging was only suspected to cause problems for Starship launches, now there's no doubt that this component, which was thought to be an effective solution for Starship stage separation, has actually contributed to difficulties for SpaceX in the rocket manufacturing process. This has finally been proven in the newest hot staging design, where SpaceX engineers decided to change it compared to the previous version. So, what problem does the new hot staging design aim to solve for Starship? Recently, we've seen a notable new hot staging design for Flight 9. Clearly, this is an important clue about how SpaceX is evolving its approach to what appears to have been one of the contributing factors behind the explosions on the previous two flights, which we've discussed in earlier episodes. As we know, hot staging offers significant efficiency gains by reducing gravity losses and allowing the upper stage to start accelerating before the booster fully separates. Elon Musk has suggested this technique could boost Starship's payload capacity by up to 10%. However, the process also introduces extreme thermal and structural stresses at the interface between the booster and the upper stage, particularly to the hot staging ring, a vented interstage designed to shield the Super Heavy booster's upper dome from the blast of Starship's 6 Raptor engines. Since its debut on IFT-2, SpaceX has continuously refined this component, using flight data to address emerging issues with plume management, booster stability, and structural durability. The latest improvements have been paying off, with Starship now delivering beautiful, clean stage separations in recent launches. But, when examined closely, hot staging still presents challenges in terms of plume flow management, booster stability, and structural resilience, which is why revisiting and refining the hot stage design is inevitable. Thanks to a new up-close image from Starship Gazer, we can now clearly see some of these changes. Huge thanks to Starship Gazer for always providing the space community with such incredible, direct photo updates. Be sure to support him by following his X or YouTube channel. One key visible change is the partial covering of the vent openings in the hot staging ring. These openings, originally designed to vent superheated plasma safely during engine ignition, have now been selectively closed off in certain areas. This suggests a shift in SpaceX's strategy for managing plume behavior and handling structural loads during stage separation. So, why cover the vents? Covering certain vents reduces the number of paths for the exhaust gases to escape, potentially allowing SpaceX to better control the direction and intensity of the escaping plume. This can help minimize turbulence around the booster and reduce heat exposure to vulnerable areas, particularly the Super Heavy's upper dome, which has shown signs of wear in earlier flights. At the same time, by retaining more material in the ring's structure, SpaceX increases its strength and stiffness. The ring must endure the simultaneous force of 6 full-throttle Raptor engines above it and 3 throttled center engines still firing below, an environment of intense compressive and shear forces coupled with high temperatures. Like all aerospace design choices, these changes involve trade-offs. Additional material strengthens the ring, but also increases its mass. For a launch system already fighting to maximize payload capacity, every kilogram matters. Previous flights dealt with this problem by jettisoning the hot staging ring during descent, shedding mass to improve booster recovery prospects. While effective, this compromises reusability, a core goal of the Starship architecture. The Flight 9 design seems to strike a new balance. Accept a slightly heavier ring in exchange for improved durability and control, likely enabling it to survive descent and recovery for potential reuse. This is consistent with SpaceX's broader strategy of refining Starship hardware through incremental, data-driven improvements, using flight tests not just as demonstrations, but as opportunities to gather information that feeds directly into hardware revisions. Another important aspect of the hot staging ring is its lack of cryogenic hardening. While other parts of the Starship stack benefit from being cooled by cryogenic propellants, which naturally increase material strength at low temperatures, the ring sits outside the propellant path. As a result, it relies purely on its baseline material properties and design geometry to withstand thermal and mechanical loads. The fact likely influenced the decision to reinforce the ring for Flight 9 by reducing the number of vent holes. Without the performance boost offered by cryogenic conditions, the ring must carry its structural burden entirely through conventional means. Thicker stainless steel, strategic reinforcement, and careful plume management. Finally, perhaps most intriguingly, the Flight 9 hot staging ring may serve as a preview of what's coming in future Starship iterations. Reports suggest that SpaceX is developing a fully integrated hot staging system for its Block 2 and V3 Super Heavy boosters, eliminating the need for a separate vented ring by building the venting structure directly into the booster's upper section. Such an approach would reduce part count, eliminate disposable components, and further improve turnaround times between flights. However, developing an integrated system introduces new engineering challenges, particularly around maintaining structural integrity and managing plume dynamics within a permanently vented interstage. Overall, the incremental changes seen on the hot staging ring of Flight 9 could serve as a testbed for future systems, providing valuable data on how adjustments to vent placement, structural thickness, and thermal loads affect the vehicle's overall performance. For now, hot staging hardware has already been installed on the booster, ready for stacking shortly. We'll have to wait and see how this new hot staging design performs on the upcoming flight. What do you think about this unexpected design change? Please give your opinion below in the comments section. While Starship upgrade operations for the next flight continue to draw attention at Starbase, SpaceX is also actively moving forward with plans to expand Starship infrastructure in Florida. SpaceX is making a transformative investment in the future of American spaceflight, with the construction of a $1.8 billion Starship manufacturing and launch complex along Florida's Space Coast. The ambitious project will see the creation of a vast Starship assembly facility known as Gigabay, alongside 2 new launch pads that together represent a major strategic expansion of the company's deep space launch infrastructure. Site preparation for the sprawling 46.5 million cubic foot Gigabay facility is already underway, with full-scale construction set to continue through 2026. When complete, the facility will stand 380 feet tall, making it one of the largest vertical rocket assembly buildings in the world. Situated adjacent to SpaceX's existing Hangar X complex at NASA's Kennedy Space Center. The new facility will be responsible for assembling both Starship upper stages and Super Heavy boosters before their rollout to nearby launch sites for orbital missions. As part of this expansion, SpaceX is constructing 2 dedicated Starship launch pads, one at Kennedy Space Center and another at Cape Canaveral Space Force Station. In the coming months, construction crews will install advanced deflector systems on both pads, critical infrastructure designed to manage the intense thermal and acoustic loads generated by Starship's massive Raptor engine array during liftoff. These deflector systems will also deliver high-volume water suppression during launches and vehicle landings, a key technology for mitigating potential pad damage and environmental hazards associated with Starship's methane and liquid oxygen propellant mix. Florida officials have been quick to frame the project as a landmark achievement for the state's aerospace sector. Rob Long, president and CEO of Space Florida, hailed the Gigabay project as a pivotal development that positions Florida as the world's preeminent hub for aerospace commerce and launch operations. It builds on the foundation we've laid over the past decade and accelerates our vision for the future, one where Florida is the choice for the best minds, the boldest innovators, and the most forward-thinking investments, Long said. He emphasized that sustainable success in space requires a comprehensive approach to infrastructure, strategy, and talent, areas in which Florida is actively leading. Before full-scale launch operations can commence, SpaceX must complete an environmental impact review process for Starship flights from both facilities. The U.S. Air Force is spearheading an environmental analysis to assess the potential consequences of large-scale methane-fueled rocket operations on the surrounding ecosystem, local air quality, and community safety. A draft report detailing SpaceX's operational plans and their environmental implications is expected later this year, followed by a formal regulatory decision on whether to grant operational approval. The proposed Starship operations have not been without industry opposition. United Launch Alliance, ULA, the Boeing-Lockheed Martin joint venture that currently manages military and commercial launches from Cape Canaveral, and Jeff Bezos's Blue Origin have both voiced concerns over Starship's presence in Florida, citing risks of explosive failures and potential damage to adjacent infrastructure. These objections echo controversies in Texas, where early Starship prototypes suffered multiple high-profile failures at SpaceX's Boca Chica test site, prompting environmental pushback and regulatory scrutiny. SpaceX, for its part, views these flight failures not as setbacks, but as valuable learning opportunities essential to the rapid development of a next-generation, reusable launch system. The company maintains that its aggressive test campaign, coupled with strategic infrastructure expansion in Florida, is key to achieving its long-term goal of creating a sustainable, multi-planetary transportation system. The Florida Gigabay project is also expected to deliver significant economic benefits to the region. By 2030, the facility is projected to create approximately 600 new, full-time, high-skilled aerospace jobs. This East Coast expansion complements SpaceX's ongoing construction of a second Gigabay at its Texas headquarters, with both facilities slated for completion by the end of 2026. Notably, the Florida Gigabay will dwarf its Texas counterpart in operational capacity, boasting more than 11 times the square footage of manufacturing space, 19 additional integration work cells, and more than double the lifting capacity. This dual-site strategy will enable SpaceX to increase Starship launch rates, improve operational redundancy, and accelerate the pace of both crewed and uncrewed missions to low Earth orbit, the Moon, Mars, and beyond. Florida officials have been eager to champion this surge in launch infrastructure investment. In 2024 alone, the state recorded 93 space launches, a sharp increase from 74 in 2023, and officials anticipate setting new records in the years ahead. Governor Ron DeSantis has highlighted Starship's potential to become the world's first fully reusable, rapidly refurbishable, heavy-lift rocket system capable of transporting both crew and cargo to destinations throughout the solar system. Florida Department of Transportation. Secretary Jared Perdue called SpaceX's investment a resounding victory for Florida's space economy and a confirmation of the Space Coast's position as the epicenter of American aerospace innovation. As SpaceX's Starship program moves steadily toward operational readiness, the Gigabay project in Florida represents a critical milestone in the company's strategy to scale launch operations and realize its multiplanetary ambitions. If successful, the facility will serve as a cornerstone for Starship missions over the next decade, supporting the assembly, integration, and refurbishment of vehicles designed for humanity's next great leap beyond Earth. It's almost the end of April, but the next Starship flight still shows no sign of taking off and has even been delayed. But why? Didn't SpaceX have a series of successful tests with Starship and Super Heavy before this? So, what happened? What problem is SpaceX facing with Starship right now? The preparations for Starship Flight 9 have been marked by intense anticipation from both the aerospace community and spaceflight enthusiasts around the world. After the mixed results of Flights 7 and 8, which revealed persistent challenges with the durability of the heat shield, the integrity of the engine bay, and overall flight reliability, expectations for Flight 9 have never been higher. Many see this mission as a crucial milestone, not only to validate recent upgrades, but also to restore confidence in the Starship program's progress toward full reusability. Initially, there was cautious optimism that Flight 9 could launch as early as late April, based on SpaceX's historical turnaround times and the relatively quick pacing between previous launches. However, as technical issues surfaced and delays began stacking up, it became clear that the road to a fully successful Starship flight would demand more patience, precision, and further refinements. Recently, an internal update revealed that the launch of Starship Flight 9 won't be happening this month, and here's why. Let's start with Booster 14. Booster 14, B14, has been one of the most closely monitored components in the lead-up to Starship Flight 9. On April 3, 2025, B14 completed a critical static fire test at Starbase's orbital launch pad, firing 29 of its 33 flight-proven Raptor engines. This marked the first time SpaceX tested a reused Super Heavy booster for a reflown mission. However, delays in moving B14 to the Mega Bay for final refurbishment after the test have raised concerns among observers. The extended stay at the launch site suggested possible post-test inspection issues or minor repairs needed to ensure flight readiness. Speculation about engine performance or structural integrity began to surface, especially considering the booster had endured intense thermal and mechanical stress during its previous flight's complex hot staging maneuver. Fortunately, images of the hot staging ring and engine section shared via posts on X didn't reveal any significant damage, helping ease worries about the need for major refurbishment. While Booster 14 seems to be progressing positively, the main character, Ship 35, has found itself bogged down by delays at nearly every step. Ship 35 successfully completed its cryogenic proof test on March 11th to 12th, 2025, at Starbase, verifying structural integrity under extreme temperatures. However, in the following days, hardware installation proceeded at a slower than expected pace, with critical components like the aft flaps not installed until nearly a month later, on April 8th. Signs of further movement appeared on April 13th, when S-35's engines arrived at the production site along with a lift mechanism, typically a clear indicator that engine installation and vehicle stacking were imminent. Yet, despite these promising developments, Ship 35 remained largely idle for weeks, with no significant hardware moves or announced milestones achieved since mid-April. As a result, delays at this point seem inevitable. But for us space enthusiasts, there's no reason to be discouraged. SpaceX is opting for a safer, more cautious path this time to secure the best possible outcome without mistakes for this Starship version 2 launch. After issues in prior Starship flights, SpaceX has adopted a noticeably more meticulous approach to system checks and hardware upgrades ahead of Flight 9. One of the clearest areas of improvement has been the ship's heat shield. Visible changes on Ship 35 indicate a partial redesign, with modifications aimed at increasing durability during re-entry, a direct response to the tile losses and thermal damage seen in earlier missions. This new configuration is expected to offer better protection under the high-temperature, high-velocity conditions of atmospheric re-entry. Additionally, the engine bay has been a major focus of evaluations and upgrades. Persistent problems with vent ports, fire suppression, and fuel plumbing during previous flights pushed SpaceX engineers to carefully review these systems. It's believed that new components and design adjustments are being integrated into Ship 35 to address these vulnerabilities, ensuring safer engine operation and reducing the risk of anomalies during ascent and descent. Beyond these high-profile areas, SpaceX has also increased the rigor of inspections on other critical systems, including detailed checks of fuel tanks and structural elements after cryogenic testing. Each verification step appears far more deliberate and methodical than in earlier campaigns, signaling a clear shift in strategy, prioritizing comprehensive system validation over fast turnaround times as the Starship program edges closer to achieving consistent, reliable orbital flights. All these measures naturally extend the timeline, explaining why S-35 has yet to move. And once it does, there's still a long road ahead. Multiple static fire tests, extensive post-test inspections, payload system installations, and the integration of the flight termination system. Only after these are complete will S-35 and B-14 be transported to the launch site. Even then, both vehicles must pass a wet dress rehearsal to confirm full readiness, followed by final system checks. Besides that, let's not forget that SpaceX is still conducting the investigation into Starship Flight 8 under the supervision of the FAA. That is also one of the reasons why the Starship launch schedule was delayed. The FAA, tasked with ensuring public safety in commercial space operations, initiates these investigations whenever a launch results in an unplanned event, such as the rapid unscheduled disassemblies, RUDs or explosions, experienced by ships 33 and 34 during ascent in those flights. These incidents, attributed to issues like harmonic oscillations damaging propellant systems, triggered mandatory reviews to identify root causes and ensure future launches pose no risk to the public, property, or airspace. The investigations are a critical regulatory hurdle, as SpaceX cannot proceed with Flight 9 until the FAA verifies that corrective actions have been implemented and approves a safety determination or updated launch license. The FAA mishap investigation process is thorough and structured, beginning with SpaceX notifying the agency within 24 hours of the incident and collecting data like telemetry, video, and debris to analyze the failure. SpaceX then conducts a root cause analysis to pinpoint the issue for Flights 7 and 8, likely vibrations or leaks leading to engine fires and explosions. The company proposes corrective actions, such as reinforcing Ship 35's propellant lines or engine bay shielding, which the FAA independently reviews to ensure adequacy. For Flight 7, the investigation closed after SpaceX implemented 11 corrective actions, but the Flight 8 investigation remains open, with corrective actions still under review. This ongoing process delays Flight 9, as the FAA requires assurance that Ship 35's modifications address the issues from both flights before granting approval. So, when is the expected timeline for FAA approval of Starship Flight 9? If we consider SpaceX's current work pace and the ongoing investigation into the previous explosion, the most likely window for approval would be around mid-May. Typically, an investigation by the agency can take anywhere from several weeks to a few months, depending on the complexity of the issues and the corrective actions required. However, if the findings are finalized sooner, the approval could come even earlier. Let's hope mid-May turns out to be the perfect window for a successful 9th Starship flight. What do you think about this updated timeline? Drop your thoughts in the comments. We'd love to hear from you. The success of this flight would move the company one step closer to its ultimate goal of achieving orbit with Starship, something previous flights have fallen short of for various reasons. Once SpaceX can prove Starship's ability to reach orbit, its initial missions will focus on validating the technologies needed for the lunar lander variant and launching larger versions of its Starlink satellites. That would keep Starship busy for the next several years, but assuming SpaceX succeeds in meeting its cost, performance, and launch cadence goals for Starship, there will be far more capacity available on the market by the end of this decade. People have been thinking about ways to use Starship for a while now. For example, commercial space station developers see it as a cost-effective way to launch large station modules. One such company, Starlab Space, envisions launching its entire station aboard a single Starship. NASA is also exploring concepts for its future Habitable Worlds Observatory space telescope that could take full advantage of Starship's capabilities. As Starship inches closer to operational flights, more and more people are coming up with ways to utilize this powerful vehicle. Some applications are fairly practical, like supporting pharmaceutical and semiconductor manufacturing in space. Others are more speculative, like mining helium-3 on the moon, or even from gas giant planets for fusion reactors that don't exist yet. Starship could also enable massive robotic missions that would otherwise require multiple launches. For instance, Starship could one day deliver a 27-meter-wide balloon to Venus. This balloon would gather atmospheric samples and store them in a 2-ton ascent vehicle, which would then launch from Venus's atmosphere and return the samples to Earth. A groundbreaking Venus atmospheric sample return mission. This concept was studied under NASA's Innovative Advanced Concepts program in 2023, aiming to mature the necessary technologies for a mission in the 2040s. Others are working to fill the current gap in Mars exploration plans. George Lordos, a research scientist at MIT's Department of Aeronautics and Astronautics, pointed out that Starship's performance could support much larger Mars expeditions than NASA's current concepts, which envision 4 astronauts or fewer on the surface. He advocates for larger crews. While more expensive, they could accomplish much more scientifically, much like research stations in Antarctica. The challenge, of course, is not only getting them to Mars and back, but also sustaining them while they're there. A team at MIT even developed a concept for a large Mars base called Pale Red Dot, which won a NASA student competition in 2023. The idea involves modular habitats that could be linked together to form 2 villages hosting a total of 36 people. In this architecture, Starship would deliver the habitats, 2 per vehicle. A system called a star crane would lower them onto skateboards on the Martian surface, which would then move them into position. The habitats would feature a rigid lower section and an inflatable upper section to maximize living space. The idea is to build large villages, maybe 30 modules per village, Lordos explained. Every crew member would have their own small studio apartment. Other modules would be designed for specific functions, including one with a swimming pool in its upper level. The lower level of that module would serve as a shelter during solar storms, with water acting as a radiation shield. That shelter, conveniently, would also be the 10-forward bar. It's a vision for Mars with abundant energy, water, food, and crew time, he said. We'll no longer be constrained by how much mass we can send to Mars. Our space industry is SpaceX and Starlink. SpaceX is far ahead of China. But if you look at the number 3 on down, it's all China. There is a much broader and deeper bench in China than you realize, said Blaine Kershaw, a member of the U.S.-China Economic and Security Review Commission, during a hearing in April about China's space ambitions. That's a very confident statement when it comes to assessing China's current space development. But will that confidence be enough for China to surpass SpaceX in a short time? I bet it won't. So, why? China is going all in on commercial space, and the numbers are starting to grab serious attention in financial circles. With a projected market value of over $900 billion by 2029, China's space industry is shaping up to be one of the country's boldest bets, not just in science, but also in innovation, global business, and technological independence. Right now, China is racing to roll out reusable rockets, build new launch facilities, and funnel billions of dollars into private companies to close the gap with SpaceX. These engineering feats promise to slash launch costs and ramp up mission frequency, democratizing access to space. By 2025, China aims to debut 6 reusable rocket models, with Zhuge 3 from Landspace and Kinetica 2 from Cassie Space leading the charge. Zhuge 3, capable of carrying 20 tons to low Earth orbit, is designed to rival SpaceX's Falcon 9, while Kinetica 2 targets cost, competitive commercial launches for both domestic and international clients. Other players, like Deep Blue Aerospace, are testing reusable landing technologies, with ambitions for suborbital tourism and cargo missions. This is all part of Beijing's bigger push to build a self-reliant tech ecosystem, free from Western dependence. Billions of dollars are flowing into private startups like Landspace, iSpace, and Galaxy Space, which are pioneering rockets, satellites, and communication networks. New launch facilities, such as the commercial spaceport in Hainan, are being built to support a surge in private missions, freeing up military sites for strategic purposes. Meanwhile, companies like Galaxy Space are developing satellite constellations, Guowang, 13,000 satellites, and 1,000 sails to deliver global broadband, challenging SpaceX's Starlink. These efforts are bolstered by government subsidies, contracts, and policies encouraging private innovation. By nurturing this ecosystem, China aims to serve its massive domestic market of 1.4 billion people while exporting space services to allies across Asia, Africa, and Latin America, cementing its role as a global space power. As tensions between the United States and China escalate over trade, technology, and global influence, space has emerged as a crucial battleground for asserting dominance. China's space program is a direct response to Western restrictions, including U.S. sanctions limiting access to advanced chips and software. By developing homegrown technologies, China aims to bypass these barriers and showcase its strength on the global stage. Its satellite deals with nations like Malaysia, Kazakhstan, and Brazil are part of a Space Silk Road, extending the Belt and Road Initiative into orbit. These agreements provide developing nations with affordable internet, Earth observation, and navigation services, fostering alliances and countering Western influence. For China, space is both a shield, ensuring technological sovereignty, and a sword, amplifying its global reach and challenging the U.S.-led order. However, to be honest, no discussion of China's space ambitions is complete without addressing SpaceX, the trailblazer that redefined the industry. In 2024, SpaceX's Falcon 9 handled over half of the world's orbital launches, with some rockets reused up to 26 times, setting a benchmark for efficiency and reliability. By contrast, Casca's 51 launches relied on expendable rockets, highlighting China's technological gap. Yet, Chinese companies are closing in. Engineers trained at top universities and seasoned by national space programs are driving rapid innovation. Startups like Landspace have already achieved orbital launches. Deep Blue Aerospace is even selling suborbital tourism tickets for over $100,000, echoing Blue Origin's model. While SpaceX remains the pace-setter, China's blend of private ingenuity and state support could make it a formidable rival by 2030, especially if projects like Zhuke 3 and Guowang meet their milestones. So, the billion-dollar question is, can they catch up? To be fair, China has been remarkably successful in building domestic capacity over the past few decades. Despite its momentum, China's space industry faces significant hurdles. China's previous successes in catching up with foreign manufacturers often involved Western companies shifting production to mainland China in pursuit of higher margins from cheaper labor, a move that inevitably led to technology transfer. But that approach won't work for space technology. There was some U.S.-China space collaboration in the 1990s, but after the 1999 Cox Report raised major concerns about technology transfer to China, regulations were tightened dramatically. And since 2011, the Wolf Amendment, inserted into every U.S. appropriations bill since, has prohibited NASA from engaging in bilateral cooperation with China. Satellites and launch vehicles are also heavily regulated under both the International Traffic in Arms Regulations, ITAR, and Export Administration Regulations, EIAR, requiring export licenses. Industrial espionage efforts are no doubt ongoing on many fronts, and likely achieving some results for China. However, by the time China's launch providers catch up to where SpaceX is today, the American company will have already moved even further ahead. China faces an uphill battle in achieving technological dominance over U.S. launch providers, at least as long as pioneering innovation remains as profitable as it currently is for SpaceX. On top of that, there are structural challenges in China's rocket development process. Development cycles for new Long March rocket generations tend to be long, much like traditional defense contractors in the U.S. and other state-backed providers like Arianespace in France or Roscosmos in Russia. KSC and CASIC have also been historically more conservative with technology rather than racing to modernize. This is a stark contrast to other Chinese industries, where private firms have made bold, state-backed bets to enter industries and eventually pull ahead. Unprepared for the disruptive innovation SpaceX unleashed, many of China's next-generation Long March rockets are now in their final development stages, with enormous resources already committed. Despite being unlikely to compete with modern reusable VTVL, vertical takeoff, vertical landing, rockets, the past decade has seen a push for greater commercial breakthroughs in China's launch vehicle sector, with frontrunners like Orionspace, Landspace, Galactic Energy, and iSpace. However, none of these companies have yet developed heavy-lift or super-heavy launch vehicles, those starting with payload capacities over 20 tons. Most of China's commercial launch providers currently operate with payloads under 1 ton, though Orionspace's Gravity 1 has a LEO payload capacity of 6.5 tons, and other rockets are in development. These companies also lack the autonomy to pursue their own ambitions in space. Instead, they've been given room to compete and develop within infrastructure and parameters set by the central government. Perhaps due to these government pressures, these space companies have mostly focused on copying SpaceX in an effort to catch up, rather than conducting deep original research, which has led to some major setbacks during testing. For example, Space Pioneer's Tianlong 3 suffered a dramatic failure in 2024. Landspace's first Zhuge 1 launch failed in 2018, and OneSpace's OSM veered off course in 2019. It's not just the rockets being copied. Even SpaceX's infrastructure, specifically Mechazilla, has been imitated by a Chinese company with about 80% similarity. The difference, when comparing images, is that China's version appears smaller and much more rudimentary. To support increased orbital launch capacity, China has gradually improved its spaceports. While its first 3 spaceports were built deep inland, beyond the reach of sabotage and foreign surveillance, priorities have now shifted toward efficiency. China's newest spaceport is located at Wenchang, operational since 2014 on Hainan Island in the South China Sea. Instead of transporting rockets long distances by rail from inland manufacturing hubs, launch vehicles can now be shipped by sea, enabling the transport of much larger rockets. Wenchang's proximity to the equator also reduces the energy required to escape Earth's gravity. China's Tianwen-1 Mars mission was launched from this facility. On January 25th, construction began on the second phase of a commercial launch facility at Wenchang, featuring 2 new liquid-fueled rocket pads aimed at alleviating bottlenecks in launch access for commercial space companies. The 5-meter diameter Long March 10 rockets carrying crewed lunar missions are also planned for launch from Wenchang, with a crewed lunar exploration site currently being built within the same complex. Despite these moves toward commercialization and ambitious new launch capacity, the fundamental weakness of China's space industry remains, developing in a slow, staged manner, heavily reliant on clear, existing examples to follow. This has made the industry less adaptable than it needs to be for the current moment, and perhaps even less capable of charting its own course without a roadmap drawn by those ahead of it. The institutions overseeing technology development are structured for long-term, gradual advancement along set patterns, and are not easily retooled for rapid innovation. China's rapidly expanding and increasingly sophisticated workforce undoubtedly harbors brilliant, unconventional minds, individuals with the potential to rival the genius of history's great innovators. However, the nation's space industry, tightly interwoven with state control and national security priorities, often stifles the kind of creative autonomy that fosters groundbreaking innovation. Unlike the decentralized, risk-tolerant environment that empowered figures like Musk in the United States, China's hierarchical structures and emphasis on collective stability tend to constrain the free-spirited ingenuity needed to push the frontiers of space exploration. The question remains whether China's elite can enact the institutional reforms necessary to emulate the United States' recent success with privatization, which has unleashed a wave of innovation through companies like SpaceX. Such a shift would require not only a restructuring of bureaucratic systems, but also a cultural leap toward embracing calculated risks and individual initiative, qualities that have historically been at odds with China's centralized governance model. Alternatively, China could choose a bolder, albeit riskier path, entrusting its national space program, a cornerstone of its geopolitical and technological ambitions, to a single visionary leader. Handing the reins of such a critical national asset to a figure who might be seen as politically unreliable would represent an unprecedented gamble for China's leadership. The space program is not merely a scientific endeavor, but a symbol of national pride and a pillar of security, making any move toward decentralization or individual empowerment fraught with challenges. That's all for today's episode. Thank you so much for watching.